share my screen. You see my screen?
Yeah.
Yeah.
So I'm gonna maybe paste the link in the chat. The chat or the Q&A? I don't remember the
Q&A, but the link should be there already, I think, because we use the same meeting room for each meeting.
Okay.
I think you posted the link last time.
Just gonna put it in the chat for now.
Sure.
Tell me if it works on your side.
Works for me.
Yeah.
We're good. So let's dive into it. Okay, so the last time I proposed to explore that paper, which is quite recent, I think it's this year, I believe. It's making a overview of different ways to encode an image. So they are covering multiple encoding schemes and discussing in particular what we call compression, so circuit compression and not image compression. But we'll see after that it's probably related anyway. So what's the goal? The goal is to take, so in the paper we are looking at a square image, so 2 at the power of m. So you have n pixels, which is 2 at the power of 2m, because of the 2 dimensions. So we are looking mainly at what we call grayscale images, so image for which the values are encoded on 1 byte. So values are between 0 and 225, which is what we call a grayscale image, which is the simplest way, the simplest, I would say, format for an image, at least in computer vision. So the way they do it is they use this general equation where you have qubits. So the k qubit will encode the position. So you have 2 information on an image. You have the position of the pixel. So we have here two indexes. I will be the index for the rows, and J will be the indexes for the columns. So the way they do it is that they simply take what we call the lexicographic order, which is simply, take the index of the pixels within that matrix here. So this is K. So basically, this is the position of the pixel in the image. And you have the pixel position, but you have also the value. So the value of the grayscale for a given K pixel, right? And the 2 informations is entangled with a Kronecker product here. So basically, the main representation would be that equations, and after it's how you simplify or you implement that equation. This is where you have variance in the literature, but basically they are starting from the same basic equations. So don't hesitate to stop me if you have questions, because I don't see you guys. So the way it's done is we're gonna have pixel positions. So the index K will be encoded with n qubits, and the pixel intensity will be encoded with L qubits. Okay, so that gives us this general Kronecker product between n qubits for positions and L for the grayscale value. So basically, we want to create superposition. So we're going to have an Adama product. And we're going to have also a Kronecker product on L qubit for the intensity value, the grayscale value. Okay. And we have our qubit here, qubits from the ground state 0. So this is what we call the quantum register. So with n qubits for the positions, L for the grayscale value. So the first stage would be to create superposition. So that way we can encode all the positions in the image using the n qubits. And after the second stage would be to encode the grayscale value with a unitary transform. We're going to see that it's basically a rotation. We're going to use a rotation to do that. So the encoding is really those two steps here. First, create superposition, mainly on the n qubit of positions, because the way I understand it is all the positions are superposed with the qubit register.
Yes. Samuel?
Yes.
There are two questions.
Okay.
Sadola?
I have a question. L here is this intensity qubit is the same color qubit, yeah?
Yeah, exactly. So that's a color, but it's not a color because we have one channel here, so it's a little bit. It's when it's one channel, we are talking about grayscale images, so black and white basically image. Each pixel has a value between 0 and 225 in that case. In the paper, they are looking a little bit later in the paper, they are looking at multi-channel images. So in that case, that would be RGB, what we call RGB images. So 3 channels, red, green, and blue. But basically, it's a little modification of that approach here. So today, I'm just going to look at the grayscale case, which is really the core of the encoding. And after, in the paper, they discuss a little bit how to extend to a multi-channel case, but it's really a small modification. Did I answer your question? Yeah. That's good.
And Tanya had a question as well.
Yeah.
Yeah, I was wondering about the unitary.
Yeah.
Is it are the qubits which are the pixel intensity qubits controlled by the position, the qubit?
I think so. That's part of one of my questions. Maybe you'll see with the circuit after. I think we'll see that there is a synchronization between the pixel value and its position in the circuit.
Okay.
So we use a special CNOT, which is I discovered with that paper. I was not aware of that particular circuit, but it's where I have a few questions. In fact, so let me show you. Just like a good professor. Recall on what is the Hadamard. So the Hadamard is really the superposition of states where we have equal probability. When you put a 0 state, you get a superposition of 0 and 1. So we create superposition of the states. It's basically just that. So of course, you can use one Hadamard, but in our case, we're going to use multiple Hadamard for each of the qubits. So we're going to create a huge superposition of states by using Hadamard on each of the qubit. So when you do that here, you get a superposition of 2 at the power n states. That's the power of quantum, if I understand correctly. That's where the magic happens, because you just have n qubits, but you get 2 power n states just with n registers. So you create a complete superposition of all the states. And this is where you get the power of quantum. This is where you should inject a processing eventually to boost some of the states. But that's beyond the paper. Just the core is to create superposition first. So what about the grayscale value encoding? So they are using, so this is called, the equation I just shown before in the paper is called the flexible representation of quantum images, FRQI. This is really the equations I've shown, this one. So this is FRQI. They call FRQI in the paper. So the encoding of the value will be a rotation, a simple rotation of the qubits. So the way we do it, they take the grayscale. So GK is the grayscale value for the pixel K. Okay. So we simply normalize K will be the maximum of the dynamic of the image. So in our case, that would be a 255, right? And we encode between 0 and pi over 2 to have an angle for the rotation. So this is basically the way they're gonna encode each value for each pixels. Okay, so the way they're gonna do it is if they're gonna use the qubit dedicated to the grayscale value to create superposition of all the grayscale values in that particular qubit. That's my understanding. So the way they're gonna do it, it's each grayscale value. So this is pixel 0. It's encoded as it's encoded as a rotation, and you're gonna have the product of all those rotations for the n pixels in the image. So the rotation is basically this matrix. So this is a unitary transform, of course, for rotation. The thing I was not too sure about it, that's why they added a factor 2 before. But after, when they talk about the implementation, you see that the factor 2 disappear, in fact. I'll show it just after.
I think it's because sometimes the rotation is expressed as the cos of theta over 2, and then
yes, that's it. Yeah, I understood that later when I checked the Qiskit documentation. In fact, I saw that they were dividing the angle by 2. So I think that's why we, but it doesn't change anything. It's a constant factor on all the values, so it doesn't
it's
really
basically
matter.
change your scaling if you want to do it between 0 and pi or 0 and 2 pi. That's all. So
okay, makes sense. So if we take a step back, so the FRQI is basically a combination of n Hadamard gates. Here they're using identity to just keep the channel for the colors, in fact. The grayscale values will be the n+1 channel register in the quantum register. So we get the FRQI equations I had before, and if you explode it, you get superposition of n states on the position, okay? Because I applied n times the Hadamard, so I get a nice superposition with equiprobable superposition of states. There's a Kronecker product with the 0 state here, and that will create this. I'm not too sure why they put these equations, but in fact, it's just saying that you're putting some space for the color values. It's my understanding. So when you put all the things together, you get FRQI becomes all of that. So we've added the superpositions due to the position and the rotations I've shown before, those rotations here for the grayscale value. And that gives these nice equations. So how is it implemented? They show the case for a 2x2 image, which is the smaller image you can take, so 4 pixel values. So 4 pixel values, you'll get two qubits only for the position, and the third one will be for the grayscale value, okay? So Hadamard will create superposition for the pixel positions, and you see on the channel, the qubit dedicated to the grayscale value, you get all your rotations. So we get 4 pixel values, the first one, the second one, and so on. So here it's a special gate. I didn't know this gate before, but this is a gate that will entangle grayscale values with its position in the image. Pay attention also to the color of the control the control gate. When it's white, it means it's off. When it's black, it means it's on. We'll see after how it's implemented. But basically, you see here the 4 positions possible. You get on and off on 2 positions, and you see black here, and black here. You get all the combinations of 2 by 2 doing that. So we put off to put the value of the grayscale at the right positions regarding the pixel encoding, the pixel state, in fact, the pixel position state in the 2 first qubit. So it took me a while to understand that, but so this thing here, it's called multi-control RY gates. So it's a rotation, but with CNOTs. So this is the case for just 2 qubits as a control. And you see that that's where the factor 2 is added, because otherwise we'll have theta over 2 here instead. So I think it's what you explained before, Tanya.
Yeah.
So it's a combination of 3. That's where one of the observation of the paper, it was they were saying that it's an expensive gate because it looks simple here, but in fact you have to explode it in 1, 2, 3, 4, 5 gates. So it's quite expensive. And here we just have 2 qubit for the position. But this is in Qiskit. There is a multi-control, we call that the control RY gate. So basically, this is really the rotations with CNOT kind of control. And these gates will be used for the implementation of the image encoding. So this is what I've shown just before for a 2 by 2 4 grayscale value. So when you explode each one of the control, the multi-control RY gates, so each one is exploded like we have here, it gets a little bit wild just for a 2 by 2. So each one of them is exploded here. The second one is exploded here, and so on. So for a 2 by 2 image, so 4 pixel values, you get 44 single qubit gates and 32 CNOTs. So it's quite expensive, I think. So the bad news is that it's in n squared. It's an n squared relationship between the number of pixels and the number of gates. So it's a quadratic cost, which is not a good news here. Note here that in the implementation, because we have this switch between on and off, they added an X gate. So the X gate is the NOT gate that will create a negative state. So you see it's here, and after it comes back here, and it comes back here and here. So it realized the switch between the control qubits. That's my understanding. So you see, it's just for 2 by 2. So it's quite expensive. So that's why the second part of the paper will discuss about compression. So compression will be to find ways to optimize the architecture of the circuit here and reduce possibly the number of gates, or merge them, or make it simpler. So half of the paper is looking at that specific problem. That's what we call compression. So it's where it gets really a little bit crazy. So I'm skipping the details a little bit, but what they did is that they they look at a way to modify the Hadamard to get a better operator, which is known as the Walsh-Hadamard transform. The Walsh-Hadamard transform is coming a little bit more from, it's well known in the signal processing domain because it's related to the fast Fourier transform. So this is a very efficient transform where you can use what we call a butterfly pattern that makes the computations very efficient. So it's like a cascade of the same pattern, and you can transform very quickly your input data. It's what we call the fast Walsh-Hadamard transform. So why they want to do that is that it creates a better matrix for the transform. Instead of using multiple Hadamard, they use a Walsh-Hadamard, and the Walsh-Hadamard is more efficient, or computationally more efficient. That's my understanding. So in fact, the way they do it is that they can merge CNOTs together, and they can, in fact, when you have two CNOTs, one after the other, they cancel each other when it's the same control node. So we're going to use that property to reduce the number of CNOTs. And the second property we're going to use is that when it's the same rotation values, you can compress in one rotation, something like that. So basically, when you use the Hadamard transform, this is the Hadamard transform. This is a recursive transform when you use the same kernel to go from H0 to H1, H1 to H2, is the same step that is used to go from one size to another size. So H1 is used to go from H2 to H3. This is the Hadamard transform. Okay. So when you do the Kronecker product of multiple Hadamards, you get this kind of relationship. So what is Walsh? Walsh is just a permutation and reordering of the Hadamard matrix. So the Hadamard matrix is this one. And they're going to just permute some of the indexes to get a more efficient computation, in fact. So this is what you call a Walsh matrix. And they take simply the Hadamard matrix, which is here. They apply some kind of permutation to the Hadamard matrix, and they get the Walsh matrix, the Walsh-Hadamard matrix. And each of the rows here is called a Walsh functions, and the Walsh functions is a complete orthogonal set of functions. So that's why it's related to the fast Fourier transform, because the fast Fourier transform is also an orthogonal transform. So I'm really making a high-level summary. You see in the paper there are a lot of details on that, but basically it's just a permutation of what the Hadamard, the general Hadamard operator is doing, and you get a more efficient set of functions that are orthogonal. So orthogonal is very nice, and they use a bit reversal permutation and what they call a gray code permutation. So when you do those two things, you get this matrix here that will do reordering of the Hadamard, and you get the Walsh-Hadamard matrix. So if you take the case for the H4, which is so a 4x4 Hadamard, normally you get that. And Walsh do just a reordering. You see the index, the position for the -1 and 1 have changed here. So the way it's done, if you look at Hadamard, the successive rows have 0, 3, 1, and 2 sign changes. So if you go from this rows to this one, you get three changes, and so on. So it's a little bit not very organized, let's say, to put it crudely. But when you put when you pass to the Walsh functions, you see you have 0, 1, 2, and 3 sign changes. So that's the idea of Walsh. It's a better ordering of more efficient projection That's the main idea. So the fast watch Hadamard transform is a very efficient transform. It's really related to the fast Fourier transform. So it's always the same pattern here that you're going to use to do the fast wash Hadamard transform. And it's just a reordering of the operations, in fact. And the gray code is a way to organize the values, my understanding. Those are really in the field of mathematics and signal processing and everything related to, there's a field in math, I think it's called approximation functions. It's everything related to theory of representations, fast Fourier transform, wavelet transform. Anyway. So the other observations is that some angles are very small. So when we do these successive rotations, so we simplify a little bit on the notations here. Those are the rotations for the grayscale values. If they are small, they won't change that much the states. So what they're saying, we can remove them. And when we remove them, we get that. And there is a property with the CNOT. When you get two consecutive CNOT gates that have the same control qubit, they cancel each other. Okay, and they can commute. So first you do the commutations. So this one, you go with this one, with this one. You see that two will cancel. You get just one CNOT, the last one, and the same here. Those two CNOT will cancel each other. Okay, so that's the way they're gonna compress the size. What we call the depth of the circuit, so the number of gates will be compressed that way. So removing small rotations. When you remove small rotations, you get CNOTs that can potentially cancel each other. That's the way we're going to do the compression. And from there, you get that circuit much smaller. Okay. So the big assumptions is that you have enough small rotations. So that will depend on the content of your image, for sure. Not all images will have that property to have a lot. Same rotations mean a lot of identical gray values in the image. So large homogeneous areas in the image. We'll see an example after. So one example is the famous MNIST dataset. So those are digits between 0 and 9, grayscale values. The image are 32 by 32, in fact 28 by 28, but they want a power of 2, so they're going to do what we call zero padding to get 32 by 32. So it's 1024 pixel values. So we'll need 10 qubits for the encoding of position and 1 qubit for the grayscale value. Okay. So before compression, it takes 2048 gates just for that image, so which is quite large. And you see, so before compression, you'll get about 1,000 rotations and about 1,000 CNOT. Okay, so it's quite large. So here we got no compression. So if we do 32% compression, the way they do it is that they take the grayscale values. So they sort the grayscale value they order them by their intensity, and they put a cutoff at 30%. So they're going to remove the 30% smaller rotations. In that image, it's not a big deal because you see, we have a lot of black background, so very small grayscale values. So it means we have a lot of identical rotations. But this is particular to this image, right? If you take another image, it's not necessarily the case. So what they did is that they apply different level of compressions. So we remove 30% of the lowest grayscale values. And you see there's really a strong reduction in number of gates here, about 40% reduction of the number of gates, but you'd get noise. So they encoded and they reconstructed the image after the encoding. So what you see here is the results of the reconstruction of the image. So you see you're adding some noise in the background because of that compression. So you're losing some what we call in the field radiometric resolution. You're adding noise to the radiometry. So when you increase that compression factor, you see that, of course, you get a very nice, we are almost at 90% compression here, but it gets very noisy because you're losing, of course, a lot of the encoding of the original values. You're removing a lot of the gates. And you can go up to 90%, which is really, really strong. And you get really a much smaller circuit, but of course you're losing the quality of the representation. So in the code, that's one of my questions. I look at the code, so we'll see the code just after. I didn't find exactly how they perform the reconstruction from the FRQI circuit. It's one of my questions on the paper. I think there is a question.
Yeah, from Sadola.
Yeah. I have a question about the reduction. This reduction happens on the last qubit, or
no? It happens on the circuits. So, well, in fact, yeah, it happens mostly on the rotations first.
on the rotation?
Yeah. So the rotations will be the grayscale value. So you decide that I don't know, under value of 10 or 20, it's 0. It's not significant. So basically, all those rotations will disappear. And when they disappear, all the CNOT are next to each other, which is also another condition because they could be in another position. So in that case, it happens that they are in the same position. So you see that the way the order encoding of the pixels may have an impact also on the compression. So if we put all the similar pixels together first, there's a better chance to compress also probably the circuit. So that's where there's a lot of I have more questions than answers after the paper, but
thank you.
You're welcome. So basically, just a summary. So we have an image that has 2 at the power n pixels here. Number of qubits will be the positions. So you have a register for the positions, so you get n qubit for the positions and 1 for the gray values, assuming that you have just 1 channel. The way they do it is they need to pre-process the pixel values using the fast Hadamard transform. So this is what I explained before. You pre-process your image with the fast Hadamard transform. And then you'll get, before compression, n, so the number of pixel rotations, entirely with n CNOTs. So it's quite costly at that stage. And the compression will consist in removing low angle values. So basically the black pixels, right? Well, I think it's the dark pixels. It's not clear in the paper. Is it around the average of the average value of the image? What is the, how do you, basically it's a thresholding, what you call a thresholding of the image. How do you perform that thresholding? I'm assuming they remove the dark pixels first. Of course, that will depend strongly on the what you call a histogram of the image, so the pixel value distribution. The example I was showing here was basically a white number on a black background. So this is perfect to do thresholding because the background is 0 anyway, and it's about 75% of your image. So it will strongly depend on the distribution of your grayscale value, in my opinion. So I've used a library that I didn't know that it's called QC Lab, Quantum Computing Lab. This is a C++ library, which is very well done, very well done. Why it's C++? It's because they do a lot of simulations. C++ is really performant for that kind of simulation on HPC computers on big clusters. So the library is very, very well done. But there is an export in Qiskit. So I'll show you when we do the computations with QCLab, you can do an export in a format that is compatible with Qiskit, and you can reload your circuit directly with Qiskit after, which is convenient, I find. I don't know if you guys know this library. I was not aware of it. No? Okay. So this is the code. Well, we can see it after. What they do is that they take it's all the steps I described just now. So you convert all the angles. You take all your grayscale value, you multiply by 2 here. So the factor 2 I've shown in the rotations. And you perform the fast Walsh Hadamard transform first. So what's going to do, it's going to reorder the pixel values. It's going to manipulate your pixel values, but this is an invertible transform. So you have the fast Walsh transform and the inverse fast Walsh transforms. The same way you have the fast Fourier transform and the inverse fast Fourier transforms, you always go back to your original values. It's just a mapping in a different space, which is more efficient because your Hadamard product, your Hadamard operator becomes more efficient in terms of computation. And you apply the Gray. I didn't explain too much the Gray permutation. It's really from the computer science sides of things, but it's a reordering of the values of the grayscale values also. So this is the pre-processing that is performed. And after they do the compression here, in fact, I think if I believe, yes, they're gonna simply remove the smaller values. So they are reordering the grayscale values, and they are taking, so the compression is like you remove 10% of the lower value, 20%, 30% of the lower pixel values, and you put them to 0 here. Okay, so this is the compression, it's just that. And after, that's where they push, they are creating the circuit. So they're going to push the rotations. For each of the grayscale values, we're going to create a rotation gates. And after, it's where it gets a little bit complicated. It's where you put your CNOT. So they use, because the Hadamard, the Walsh Hadamard transform is similar to a fast Fourier transform, you can easily plan for your CNOT gates. That's where I understand, because this is an iterative transform that you apply. It's called a butterfly in the field, a butterfly pattern, but it's always the same pattern. So this is a quick way to put your CNOT entirely with your rotations. Otherwise, it could be very tedious to do the building of the circuit, right? Because you have to put your control gates on and off, put your CNOTs on multiple levels, and put your rotations. So this way, so basically what you have to understand is the fast Hadamard transform is an efficient way to build your circuit. It's just that.
Samuel?
Yeah.
And I guess this works because of the fact that they use a gray code to.
Yeah. Yes. Also. Yeah. Yeah. It takes a. I'm not too familiar with those techniques, but they are very well known in the field of signal processing to efficiently process signals and do transformation. Very similar to the fast Fourier transform, in fact.
Yeah, because I think the difference between one pixel and another that is right beside it is only one binary difference, basically. So if you have a binary chain, there's only one difference between two chains of 2 pixels which are next to each other.
Yes, right.
I guess they depend on that to
Yeah, but you see, like the intuition is that when you look a little bit of the, you see, it's a little bit messy, right? When you go from one row to another. Here you see a pattern when you go from one row to another. You see there is blocks that are divided by 2 here.
Yes.
And so that's the butterfly pattern, in fact, that they use in fast Fourier transform. You go from one row to another with a simple transformation. So that way you can organize your circuit in a very efficient way. And it takes just a few lines of code. That's my understanding. That's the main idea. You have to, the math is a little bit complicated, but the main idea is quite simple. So this is basically the fast Walsh-Hadamard transform, which is a few lines of code. It's not very complicated. And you see, you take the average between the values, you take the difference. It's very similar also to the R transform, which is a kind of wavelet transform, which is also a cascade of operations. But that's well known in the computer science. So we can, if you guys are up to it, I made a small notebook that shows how to use the code. So we can maybe look at it. I didn't completely finish the code, but just a start. So basically, here I shouldn't have done it, but it's not the right way to do it. Don't put your token of your account in in a notebook because everybody's going to use it. But basically, this is the token coming from the Qiskit account to get access to the API. So I'm going to try to use it. We don't need a GPU here, but anyway, I don't have it. So here we're going to install Qiskit. Can show the code. It's basically Qiskit, a few useful libraries, but mostly Qiskit here. So after we're gonna do some import, set up your API token. So if you have one, use your token. The good way to do it is to have an environment file that you load after. That's the right way to do it, instead of putting that in a cell. But I didn't follow my own example. So here I'm loading the environment. I'm just connecting to Qiskit. Here it's a choice of the backends. So it's typical of Qiskit. I think I'm getting an error here probably, but doesn't matter at that point. And here I started, but I didn't finish, is the way to build the circuit if you wanted to do the FRQI with a 2x2. So basically you use 2 qubits as a register for the position. The third one will be for the, but it's not finished. I didn't have time to finish. What I wanted to show you, that's something I could finish later on probably. It's simply, so the library is called QPixel. So it's coming with the paper and it's based on QClab. Just I wanted to show you. It doesn't take 12 minutes. It depends. The last time I did it, it took me 17 seconds. But it depends on your instance on Google Colab, I think. So here, I don't know. It's a little bit a lottery. I'm not too sure. Because this is a C++ code, it takes it can take a few minutes to compile. And they are using a lot of C++ templates. So it's a library that is very efficient, but that could be, it's known to take a few minutes to compile, usually. Just I want to warn you. But once it's compiled, just I want to show you, you can run the test. And you get a compressed FRQI. So the compressed FRQI will replicate the results I've shown you in the slides with MNIST. And you can run different compressions level on your image. and that will run basically the experiments in the paper. So that's interesting for that. So it's going to take, I think, a few minutes. So this is an example of one of the images that are shown in the slide. So this is the kind of MNIST digit. So this is a 32 by 32 image, grayscale. You see that the histogram, so the distribution of the values, very conveniently, it's a lot of zeros, okay, because you have a black background. So if you want a threshold at 30, 50%, it's not a problem. It goes all on the zeros mostly. So that's where it's a little bit, the evaluation I find a little bit biased in that regard, because this image is really, it's a particular case that fits a little bit the scenario of a compression of smaller grayscale values. But if I have one criticism to make, I'm just going to check if, well, you see I'm in the 12 minutes scenario. Anyway, you can run on your side. So the way you do it is that you run compress FRQI on one image. So they provided a few image in grayscale format, and you provide your level of compression. So here I've put 50%. And the one I believe is to do the simulations to reconstruct the compressed image. So that gives you each time the statistics of your circuit. So it's constructing the circuits for you. It's using 11 qubits, so 10 for positions plus 1 for grayscale. That gives you the total number of gates of CNUTs, RY, and your compression settings, and you get what I've shown in the slide, the compression ratio for each of your type of gates. So they're using a format that I didn't know. It's called the OpenQISM2 format, which is a way to encode circuits that is compatible with Qiskit. So in fact, it's gonna build the circuits and write it in a .qasm file, and that .qasm file you can reload it in Qiskit, because as I explained, the circuit is quite large and quite deep. So the fact that you have done it in C++, that's a big gain. If I wanted to replicate that with Python, that would have taken me a few pages of notebooks before I get it. So you can load it with that command here, the QASM, and I can print the circuit, and you see the circuit here as a text format, and all your qubits for positions, the one for the grayscales, all your rotations, the X nodes to turn off on the control gates. And you see that, imagine that programming that in Python. So it's almost impossible. I mean, and you see that the ordering is following the fast Hadamard, the fast wash Hadamard transform. So it's optimized in that sense. But you see, I can go on for a long time. It's quite deep. Okay. And also they provided the reconstruction. That's where it's a little bit. So the reconstruction is done with the QC library, which is the C++ library. I didn't check the code, but the missing part in my presentation is how you do the reconstruction. I guess it's measurements of the states, I'm assuming. But it's a question mark for me still. But the code is here, so it's just a question maybe of. You see, it takes a little bit of time to build it, but it's working. I checked. So I think it's a nice paper. It showed me a lot of aspects I didn't know, especially on the computational aspect. How to build a very deep circuits. What are the challenges? And you really need to find tricks to optimize the way you are adding new gates in your circuits. So that's about it for me. I don't know if you have questions or comments. I can show you maybe. So in the paper, I only give an overview, but so I simplify a little bit, a lot of things, but there's a discussion. So they show the scaling, the gain of using the fast Walsh-Hadamard transform in terms of the building of the circuits. It's not about the quantum computation. It's just to build the circuits. It makes it more fast, much more faster. I didn't show that slide, but we give an example here, original and compressed. They talk about other ways to encode the grayscale values. So you can use 2 qubits if you have multiple. It's basically you are slightly changing the rotations with something else. It's just a variant of the rotations, but basically it's the same scheme. So they show the multiband also when you have RGB pixels here. In fact, you have 3 rotations in that case because you have three values for each pixel, so it makes it more costly for sure. But it's discussed in the paper also. So yeah, it's interesting. But you see, they show an example here with a bigger image, which is 256 by 256, an image that is more complex than just a black background. If you don't do compression, you have more than 65,000 2 times gates. So it's extremely deep. And I don't think it's feasible to use that probably. So they show the compression level with different level of compressions, and above 75%, you start to degrade really the pixels values. It gets really noisy beyond 90% in that case.
Marco just asked a question in the chat to know if they were comparing with decoherence times in real devices, because the circuits are very different.
No. So it's really just simulation in the paper. There are no experiments with real. I guess that would have been a disaster, I suppose. It's not. Is it feasible to have? What's the maximum depth we can achieve right now with real?
I'm not certain. I think it depends on the gates you're applying, but it's definitely less than that. In the case of the 256 by 256 image, I think even 99% of compression, even that is too deep, basically. Because you have 600 and a few gates, which are rotation gates, and then 1,000 CNOT gates, which is a lot. But this is only for encoding. So let's say we encode that to apply some kind of quantum computation on it. We would have a circuit that is appended to this circuit to do the quantum computation. And we need to keep the state coherent until the end of the other circuit.
Oh, yes. Okay.
So it's even deeper than that. I don't know if...
so I think it's very, very... I think that's why they don't talk about real quantum computers here, because they know it's really on the way to build the circuits, but knowing that it's not feasible yet.
It's interesting.
Yeah.
It's an interesting idea. But Marco says in the chat that it depends on the device and the gates, but also that CNOT gates are 10 times larger than 1 qubit gates.
Okay.
So even that 1,000 and a few CNOT gates, there's really a lot of CNOT gates. But I guess that in the case of not too big images with tons of zeros and some conditions that are, very thought through and that we compress a lot, maybe it's usable in specific case. But I'm not sure other than that. It really is.
So you see that it compiled here. It took me 8 minutes, but
Yes.
it works. And after you can you just run the test to make sure you see that everything is working fine. You can access the compress FRQI command, and it shows you how to use it. And this is an example. And you can run the compression. The compression is really fast. See, it runs really fast. And you can, so it will produce an output.qsm. You can open it if you want, but it's quite a large file. So it goes somewhere here. Here, you'll get the QSM. You'll get your output of the simulation. You see, this is an ASCII file, so this is like a Python code almost, but it follows the standard OpenQSM to define your circuits, and this is what Qiskit will understand and recreate your circuit here from that command line. So that's a nice discovery for me. I was not aware of that way to do things, but that could be useful for experiments or simulations, and still go back to Qiskit to do something else eventually. But I find it's a nice, and it seems to be well maintained by the people. So this is the University of, I think it's a research center in Europe, I believe. Just go on GitHub. Just gonna check quickly. It's a quantum computing lab, but I believe it's the same people. University of Berkeley, so it's not a bad reference. The Lawrence Berkeley National Laboratory, to be precise. So they have QC Lab and the QPixel PP, which is based on QC Lab. So that's it for me. I hope it was not too brutal, but
Thank you, Samuel. I don't know if you want to plan what we're talking about next meeting. Oh, you're muted, Samuel. I don't know if you're talking, but.
Oh, sorry, I shut down my Teams by accident. I was a little bit brutal. So yeah,
Yes.
yeah. So the next time, I don't know what's the plan.
It was very interesting. I don't know if you've seen some other avenues within the paper. I'm not sure if you.
Well, I think there's probably a way to because I come from image processing, so I know we can probably organize the pixel values before doing the encoding.
Okay.
There's an entire domain called image compression. So it's the way you can use superpixels, you can use binary tree partitions to create a cascade of pixel values for your image. So there is probably a way to represent the image in a more efficient way. Let's say not just following blindly the order of pixels as line of columns, but putting similar pixel regions first together, because we have complete control on how to build the circuits, the order of construction of the circuits. So if we can put similar regions first, so the binary partition tree of the image will give you what to put first as similar regions. That way, there's probably a way to compress the circuit, but that will take into account the structure of the image in terms of pixel values. But just an idea. It's still going to be quite a deep circuit, unfortunately, I think.
So it would mean to pre-process the image before we even do what you described today by doing something like, I don't know, wavelet transform or something to organize our different regions, basically.
Yes, exactly. It's used in the field of image compression. So when you are trying to reduce the size of the file, the size of the image file, and it's called binary partition tree. I'm trying to find an image of that. Yeah, it's a way to get a more efficient representation of your image. I have an example here. See here. So you partitions your image in segments, and you have a top-down representation of image in terms of proximity or similarity between each of the region. So 9 is the entire image, and after you have 2 segments, and after one of the segments is deeper, but you see there's a hierarchical organization of the content, and it's used in image compression. It's called a binary partition tree. But that way you have probably a better understanding of where it is the same values in the image. So there is probably a way to use that to better encode the rotations following a specific order. But it's just a quick idea. It needs to be explored a little bit more. So basically, when you take our black and white image for like the number I've shown before, you'll get at the first level, you'll get the bright pixels, the number 3, and the background, the zeros. And then you can go, but basically you could resume your image just with the first level here.
Yeah.
So you get 2 groups of homogeneous pixels, and that means that all the rotations are similar in those 2 groups. And probably that could be a good way to compress the circuit. Maybe it's just a speculation from my part, but so it's a pre-processing of image for sure. But they do already the pre-processing. They use the fast wash adama, which is transforming the pixel values. But I guess it could be that side could be explored a little bit more.
Yeah. Okay.
Yeah. So
do we meet in 2 weeks actually?
I think it would be more 3 weeks, because
Okay.
in 2 weeks we have the Geomatics Day.
Okay.
Day.
Oh yes, that's
so it's gonna
true.
like most of the people from Geomatics are gonna be in Bishop's University for conferences and workshops and stuff. And people from quantum computing are welcome if they want to join.
Yes.
But it would be more in 3 weeks, I think, at the soonest.
Okay. So in the meantime, maybe we could do some literature review, find an article that we find interesting, and if somebody says, I want to talk about this article, then you can just either write in the Teams or send an email, and we can do that for 3 weeks. In 3 weeks.
Yeah, I'll try to find something else also on my side. If I find another paper, interesting paper, I can also contribute. I was looking at quantum image processing recently, so it's basically it's what we have done today, but you add steps to extract some information from the quantum representation. So some people do edge detection, for example, but in the quantum, using the quantum representation. I didn't check how it's done yet, but that could be maybe a way to extend the discussion today.
Yeah. Great. All right. We can do that. If nobody has any other question.
I think Marco is writing in the chat.
Oh yeah.
If they run a real devices in the paper.
No, I said that's what I said before. Just simulations. They don't. They didn't touch real quantum computers. But Tanya explained that it's not. Anyway, it's not really. Yeah. Why not? Yeah. Why not? If we have access to it. Okay. Yeah, I'm game. I'm game. But I think we will need Tanya and Marco in that case. Yeah, maybe a small image that could be interesting. Maybe. Okay.
Maybe we could try their two. What was it? 2 pixels image?
2 by 2.
2 by
2 by
2.
2.
Yeah, 2 by 2.
Yeah. But maybe one option is to decompose the image in blocks of 2 by 2.
Yeah.
So you get multiple circuits that are encoding different part of the image. But I don't know if there is an advantage to do that in terms of output. But
yeah, then what to do with the 2 by 2? That's.
you can use multiple qubits to encode different part of the image. Maybe I don't know.
Yeah.
I'm just thinking out loud.
Yeah. So we could try to write a code
Okay.
that could, yeah.
And if you guys find a way they reconstruct the image, they don't talk about it in the paper. So that's I would be interested to understand how it's done. As a homework for next time. But it's I think it's in the QC lab library that is done.
Okay.
But I didn't find it yet.
Perfect. Yeah.
All right.
Cool. Thanks.
Thank you, guys. I hope it was useful.
Yeah. Thank you.
Thank you.
Merci. Thank you.
Thanks so much.
Thank you.
Bye bye.
Thank you all very much. Bye.